All right, we're moving on to our last video of section 5.1. Unfortunately, there's still more for chapter 5, but this is the last one for 5.1. We're in objective 4, which is using simulations, which we technically already did, but we're going to do it a little bit more. So suppose it takes you 2 seconds for each single toss of the coin and the die. So if you had a physical coin right in your hand and a die in your hand, and suppose it took you 2 seconds to toss them, okay? How long would it take you to perform the experiment of tossing a coin and a die 1,000 times in seconds? So you can see what I did was I said, okay, 2 seconds times 1,000 times makes 2,000 seconds. Now what is that worth in minutes? Well, you take 2,000, you divide it by 60 because there's 60 seconds in a minute, which means 33 minutes. And in hours, that's 0.56 hours, right? Because you take 33 minutes divided by 60 minutes, and an hour, there's 0.56. So nobody's got that kind of time just to toss coins and dice. I mean, unless you're really bored. You don't want to do that. I mean, what if I wanted to do 10,000 times? It'd be even worse, right? So what we do, and you saw it here, with these ones, it's not like you couldn't have done this yourself, but you don't necessarily have a 6-sided die floating around your house to do it with. And you certainly didn't want to do it 30 times and sit there and try to record every outcome, right? So we used a computer to do it for us, and that's called a simulation. You use a mathematical or physical model to reproduce the conditions of a situation or process. You collect data, often with computers, and that allows you to study situations that are impractical or even dangerous to create in real life. So nobody wants to toss coins 1,000 times. I mean, maybe, if you're really fixated on coins and dice. But most people don't want to do that, right? So you make a computer do it for you. And that helps you with some things that's just tedious. But some things are dangerous. You can't simulate, I don't know, real life people in a car crash. You can't do that. You have to simulate it, put the dummies in there and try to simulate it. That's the best you can do. So we're going to use StatCrunch to do this. So I'm going to go back to StatCrunch. And we're going to do it one more time. We've got stats, let's see, oops, it's data, I'm sorry, data. We want to sample columns. We want to sample from the outcomes column. We want 1,000. Oops, not 10,000, 1,000. Obviously, we're with replacement. We want to actually stack it. Stack it in, and in whatever column it puts it in, that's fine. All right, I'm going to do it. Sample column. And there it is. Look how fast it is. And it rolled them 1,000 times. Look, it's all in there. I swear. All right, I don't need that sample column, so I'm just going to go to columns, delete. And the one that says sample at the end, I'm just going to make that go away. Delete. And I'm going to label this so I know. This was 1,000 times sample. Okay? And actually, I'm going to select this whole column. I don't know if I can. No, I'm going to have to do it the long way. So I'm going to select the whole column, scroll down. Actually, I wonder if the Control-Shift thing works. Let me go back to the top. Nope. Oh, it doesn't matter anyway. I'm being a moron. I need to sort this thing in the first place. So I'm going to go to Edit. I'm going to go to, let's see, what is it? Oh, I'm sorry, it's not Edit. It's Sort. Under data. So go to data, go to sort columns. I want to sort that 1,000 times sample, and I'm going to say sort, and there it is, and then it's sorted. And I don't really need to label it. I think that's kind of obvious that it's sorted. All right, now in order to get this into my Excel spreadsheet, turn it in, what I'm going to do is I'm going to cheat a little. I'm going to select all, and I'm going to copy. So edit, select all, edit, copy. I'm going to go back in here. And actually, I want to kind of insert a couple columns here because those answers that I had before, I need to have space for those new columns to come in. Sorry about that. So I just went up here and I right-clicked and I inserted, and it inserted some columns for me. And then I'm going to go up here to the top left corner. I'm going to paste, and there they are. Okay. So sorry about that. You got to insert a couple spare columns so you got room for these two columns to show up. Right? Otherwise, these two column things would have been overwritten right there. All right, now I've got them in order. I can count how many H1s there are by using my mouse. I can click and drag. Drag, 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 drag. Oop, there's H2s. There's H1s. So if I lift up, you can see down here in the bottom right corner, it says there's 71 count. The other way to see it, I don't lift up on the mouse. Just look Okay, it's kind of above the yellow. There's a little box that says 71RX1C, 71 rows, 1 column. Okay, so that's another way you can do it. And there's also another feature called the count feature. So you could say, okay, number of H1. So you can say equals count, and you want to count, count if, and then your range is I1 or I2 colon I 1000, 1001. That'll be all of them, I believe, comma H1. Oops, I'm sorry, comma quotes H1. I'm sorry, it's text. It doesn't like H1. It needs to be, there you go. So count if, that's another way to do it. Just for the fun of it, was I right with 1001? Yes, I was. There you go, 1001. There you go. All right, so why am I doing that? Well, because I need it for this question. It says how many were H1s. Now for you it'll be different than for me. It's 71. So the probability here is 71 out of 1,000, which would be 0.071. Fabulous. All right, now is that the same as the classical probability? It's not the same. Let me type that. There we go. Now, was our probability here the same? No, it wasn't, right? But it's close. Oh, I probably should have found that probability here. So the probability of H1, that way it's in our Excel spreadsheet, is equal to 71 divided by 1,000. There we go. And I'll make them yellow, or I'll make them green. You can make them whatever you want. Orange, that looks good. All right, so while we're on the subject, let's make sure we save this under Chapter 5 Technology. That way it's all good and saved for later use. All right, let me go back. Oop. Hold on one sec. There we go. Closed. All right, so now we're out of simulations, so I hope you enjoyed it. It's basically making a computer do stuff for you, and there's lots of different ones. We did pretty much one of the most basic things you can do, and we use StatCrunch to do it. You can use Excel, but Excel is actually not as nice as StatCrunch for that. All right, the last topic is subjective probabilities. So there are a lot of things that we want to know probabilities for, but they're not repeatable in some way. The setup is so unique and so individual that you never can know the probability. You can kind of make an educated guess based on your past experience and stuff, but it's not like you have data, sitting there in front of you. Subjective probabilities are perfectly legitimate. A lot of people think of them as, oh, since that's based on personal judgment, it's garbage. It's like, well, not necessarily. It depends on the person making the judgment call. So for example, if I wanted to know the chances that, I don't know, Brad Pitt will win Best Actor this year, well, if I make that judgment, that's a totally different world than if, some industry insider makes that judgment, right? If I say, oh, he's got a 70% chance, and the industry insider says, no, it's more like a 62% chance, obviously you should probably listen to him. He knows more than I do, or she knows more than I do. All right, so we're going to define the following probabilities as classical, empirical, or subjective, and then we'll be all done. So the first one's the World Series of Poker. Oops, I already gave that one. So when the World Series of Poker, if you ever watch it, they'll show the person's hand, and then they'll actually attach the probability right then and there. Now it's done by computer, because a computer can know all the different possible combinations that are possible in a hand, but it's a classical probability because it's based on hypothetical models of cards, and gambling, right? I mean, in general, cards and dice are like the perfect examples of classical probability, right? So they look at the hands and go, oh, that's an ace king. He's got a blah % chance of winning. All right, what about the Red Sox and the Yankees? Now, I know you might think, the Red Sox and the Yankees, they've played a lot against each other, right? But it's not a classical thing. It's not like you can set up a hypothetical model. I mean, their results are changing all the time. Okay, so believe it or not, and I know what you want to think. I know you want to think it's empirical, but it's not. And here's why. It's not empirical because past data does not necessarily relate to the next game. in sports, I don't know why I'm putting this in parentheses. It doesn't need to be. In sports, most probabilities are subjective because the conditions are constantly changing and unable to be replicated. Okay? What do I mean by that? Well, it's not like, you can say, oh, well, the Red Sox have always lost to the Yankees, therefore they will lose again. It's not like that. It's like, well, every time they play, it's a different setup, different weather, different lineup, different conditions, different crowd, all these things affect what's happening. And if all of those things affect what's happening, then you can never really have an empirical model for it, right? It's every time they play, it's different, slightly different. So yes, you can use past data to try to help you make that educated guess, but in the end, it's an educated guess, right? As opposed to the Red Cross blood type thing, that's empirical because the Red Cross gets extensive records, and the distribution of blood types should follow the pattern seen in the data. It's not like every time a person walks in, it's the chances of them being O negative changes. It's not like that. It's, hey, the whole population, here, let me put this extensive records on the whole population. Let's put it that way. Right? They can gather data on all the people that come in and donate. They can gather data from hospitals. They know what babies are born with what blood types, right? So they gather data on the whole population. They have it all figured out for everybody. So that distribution doesn't change when a person walks in. As opposed to the Yankees and the Red Sox, they constantly change based on literally who walks in, how the manager feels that day, whatever. How you feel does not affect your blood type, right? But how you feel on a certain game day can affect your batting average, can affect your RBIs, can affect your, right, everything. Does that make sense? So in other words, the subjectivist stuff is for games that are not repeatable. You will never... That Red Sox game, that particular Red Sox-Yankees game will never happen again. Whereas people will walk into the Red Cross all the time. Okay? It's a little strange, but in general, subjective is stuff that you're just making an educated guess for. It's not repeatable. Those exact set of circumstances are not repeatable. Empirical is based on data, usually hopefully from a whole population. You can get some data, and then you can infer from there how it is for the rest of the group. For our purposes, obviously empirical is really important because empirical is how we gather data on the world. I mean, the whole point of statistics is to gather that data and make inferences. All right, we are done with section 5.1. I hope that helps, and we will move on to section 5.2 next time, which is the addition rule and complements. See you then.